Projectiles. Definition of projectiles is any object that is only being affected by gravity, and we're going to assume that there is no air resistance. That complicates things, and there are some examples with air resistance, but we're not going to be dealing with that. The three equations we're going to be dealing with when we talk about projectiles is going to be these three equations, which we dealt with before. The final velocity equals acceleration times time plus initial velocity displacement is going to be equal to 1/2 times acceleration times time squared plus initial velocity times time, and then final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. Now this is going to be important because we're actually going to be talking about velocity, displacement, and acceleration in specific directions. First of all, the acceleration is going to be, for the x direction, is going to be 0 meters per second squared. There's no acceleration horizontally. All the acceleration is vertical, which is negative 9.8 meters per second squared. So there's this one guy who is new to a city, and he wants to get to know some people, so he goes to a community center, and they say that they're all going to gather up, and they're going to go to like a hang glide territory, basically, where it's next to a cliff, and you got people out there, and they're just going to have a picnic and have some fun. And so he goes out later that day and sees all the people around, and he's not really interested in the food, but he looks around for potential friends, and he sees this one girl who goes over to a cliff, and the cliff is a little bit high up, and so she asks the question, I wonder how high we are. Well, he knows a little bit about physics, and he thinks he can answer that, but somebody interrupts him, and they go over there and says, you want to know how high we are? I'll tell you how high we are. Watch this. Alright, so a little bit of background. Displacement is going to be equal to 1/2 times acceleration times time squared. So we need to figure out the height, which is going to be how high we are. That's the displacement. Well, we know the acceleration is negative 9.8, but let's go ahead and round that to 10. So half of 10 is going to be 5, and then the initial velocity is going to be 0. So essentially we're left with this equation. Displacement equals negative 5 times time squared. So he drops the object, 1, 2, 3, 4, 5. It takes 5 seconds in order to hit the ground. Negative 5 times 5 squared. 5 squared is 25. Times 5 is going to be 125. So he knows that we're going to be 125 meters high. And she's very impressed by this, but the guy who is new in town, apparently he missed his chance. So the next day, or the next week, they go out and he goes to a different community center and say, well, we're going to go out to hang gliding territory and have a picnic. Apparently not really too many other things to do around this place. But sure enough, he sees this other girl who comes up to the cliff and says, I wonder how high we are. Well, he thinks he struck gold. He basically got the same scenario, and he knows how to answer this, but the only problem is a little bit further upstream, and instead of straight down, it's a little bit of a curve, so he drops a rock and it bounces back and back until it hits the water. And then you do your calculations, you just say, well, we're several kilometers high. Well, she thinks he's a complete putz, but what you can do instead of letting it drop is throw it horizontally. Because the amount of time it takes for an object to move horizontally is the same amount of time it takes for an object to fall straight down. Because the total the vertical velocity initially for both of them is 0. So you're going to get the same scenario. You're going to get the same amount of time each way. So that brings us to this. One with a horizontal velocity with something greater than 0. You can see that that's pushed out sideways, and then this one just drops straight down. Well, each time frame that goes by, they're at the same height the entire time. That's because the same amount of time for the object that falls straight down is going to be for the object that goes off horizontally also, because initially they start with no initial vertical velocity, even though this one has horizontal. The horizontal does not affect the vertical. So here we have a problem from the book. It says a stone is thrown horizontally at a speed of 5.0 meters per second from the top of a cliff that is 78.4 meters high. So how long does it take for the stone to reach the bottom of the cliff? So here we have a stone 78.4 meters away, and we're going to throw it horizontally 5 meters per second. It's going to make a nice little arc. So we're going to list the information we know. We know the acceleration due to gravity is negative 9.8 meters per second squared. The displacement is negative 78.4 because we end lower than where we started. The final is going to be 0. The initial is 78.4, so final minus initial is negative 78.4. Notice we use a y instead of an x to say displacement here because we're talking about the y direction. The initial velocity, well, the initial velocity is completely horizontal, so the initial velocity in the y direction is going to be 0. Well, Considering we need to find time, we're going to take displacement equal to 1/2 times acceleration times time squared plus initial velocity times time. We're going to plug in the information we know. We get negative 78.4 is going to be equal to 1/2 negative 9.8 times time squared plus 0 times time. That part's going to cancel out, and we're left with this equation. We're going to divide both sides by negative 4.9. That gives us time squared equals 16, square root both sides, and we get a positive and a negative answer, but we know the correct answer should be positive. That only makes sense that we have positive time in the future. So it's going to be 4.0 seconds. This problem, it's the same scenario except we're now, part B is going to say how far from the base of the cliff does the stone hit the ground. So we're looking for horizontal displacement. Well, we list the information we know. We know the acceleration is going to be 0 meters per second squared. We know the initial velocity is 5.0 meters per second because it was completely thrown horizontally. There is no vertical component to that. And then the time is going to be 4.0 seconds. Displacement is going to be equal to 1/2 times acceleration times time squared plus the initial velocity times time. Plug in the information we know. We know the acceleration is 0, so that part goes away. And we get 5 times 4, which is going to be equal to 20 meters. So the displacement is going to be 20 meters. That's going to be how far away from the cliff it hits. Now this measurement that we have away from the bottom of the cliff, that's called range. That's how far horizontally it's going to move. We call that range. Next part of the question, it says, what are the horizontal and vertical components of the stone's velocity just before it hits the ground? Well, if we look at this, we know it's going to have a horizontal and vertical velocity and gives it its total velocity here. We'll talk about that in a second. Since the initial velocity is 5 meters per second, we know it's not accelerating, so the final velocity is going to be 5 meters per second also. Looking vertically, we know that the initial velocity vertically is 0 meters per second. We use this equation, the final velocity, because acceleration times time plus initial velocity in the y direction. Plug in our numbers, and we get that the final velocity is going to be negative 39.2 meters per second. Now the problem doesn't ask for the total velocity, but I want to go ahead and figure it out. The total velocity is going to be equal to the square root of the final velocity in the x direction squared plus the final velocity in the y direction squared. Punch that in, you get 39.5 meters per second. And to figure out that angle, it's going to be inverse tangent of 39.2 divided by 5, which gives us 82.7. So the total final velocity is going to be 39.5 meters per second, 82.7 degrees below the horizontal. All right, so this kind of gets to this problem right here. We talk about the horizontal and the vertical velocity. The horizontal velocity stays the same the entire time because there's no horizontal acceleration. The vertical velocity, however, decreases, and it decreases at a rate of 9.8 meters per second every second. So from here to here decreases from 9.8 meters per second, and from here to here decreases 9.8. But when it's coming back down, it gains that velocity back. So it gains 9.8 here and gains another 9.8 here. So velocity downwards increasing. You can see that the hypotenuse of this angles more and more downward over here and more horizontal on this side, and then it eventually comes back around. And it's only because the vertical component is changing, the horizontal is not.